Okay, there we go. Okay, so new topic for today, directional derivatives and the gradient. Starting off with directional derivatives. The big idea of directional derivatives is that it's going to be a generalization of a partial derivative. It's the big takeaway. It's a generalization of the partial derivative. So what I want to start with is by reminding you a bunch of things we know about partial derivatives. So partial derivatives, they give you the slope of the graph. Specifically now, there's lots of cross sections to the graph. They give you the slope in the direction of the standard basis vector defined by the variable you're taking the partial with respect to. Okay, so slope of the graph in a certain vector direction. Okay, what else can we say about partial derivatives? They're a factor, right? It's what you multiply by input change to get output change. Again, with the understanding that you are moving in that same direction defined by the variable that you're taking the partial with respect to. So this is all review of things we talked about before. And now a couple of other things, and you can view these in different ways. But in some sense, you can view both of these results as sort of consequences of the chain rule, you might say. But you can view a partial derivative as being, well, it's what you get when you start at the point where you're evaluating the partial derivative, and then you move. Notice I've made a parametric line here. This is a parametric line whose velocity is the same vector, the vector that points in the direction of the axis of the variable that we're taking the partial with respect to, right? And then we look to see what is the rate of change of the function. So what is df dt? Right. So again, old news that if we're moving with unit speed velocity given by this appropriate unit vector, standard basis vector, then the partial derivative gives you the rate of change of the function. So it's a different way of writing it, but you can crank this out, by the way, if you want to directly confirm and using the chain rule, because we have f of this parametrized line function of t. You use the chain rule, multiply it out, and what you'll find is that indeed you do get this as the partial derivative. Okay. And then another formulation, and this really is straight up the chain rule, right? But the partial derivative is that dot product. Easy, of course, to see this because, this is made up of all of the partials, and when you dot with a standard basis vector, you're just going to pick out the corresponding one. Okay. Okay, so all together then, what we have here is, let's see here, and again, same standard basis vector there. We have, I'm going to say 4 facts about partial derivatives. But there's something particularly special about these 4 facts, and that is all 4 of these properties, as I've stated them here, are in reference to vectors, not coordinates. So, if you think about it, how did we define partial derivatives way back when? The very first thing when we defined partial derivatives was, hold some of the variables constant, and then the other variable, so it's all this talk about variables, right? Here we're not talking about variables. Here, I'm viewing this construction called the partial derivative and describing it algebraically, geometrically, in terms of the appropriate corresponding vector, EI. Okay, so what's the relevance of that? So what? Well, it's got nothing to do with variables anymore. This is all just statements about vectors. In fact, you might say this as, hey, there's certain computations that you can do from the point of view of, hey, what if you're looking in a certain direction defined by a certain unit vector? Well, as you look in a certain direction defined by a certain unit vector, the slope of the graph is the same as the factor you multiply by, which is the same as what this expression works out to be, which is the same as what that expression works out to be. All these things all relate to this same unit vector, EI, the standard basis vector corresponding, etc. Okay, so, alright, so what is it that's so special about standard basis vectors anyway? Rhetorical question. Standard basis vectors are nice in relation to coordinates. So if you're not interested in coordinates, There's nothing particularly interesting or special about standard basis vectors. They're just just run-of-the-mill unit vectors, really. So I would like to propose, now this is not a proof, and I'm not going to prove the results that I'm about to assert. I just want a plausibility argument, digestible, intuitive satisfaction, perhaps. But I just want to make a pitch that if we've got all these things connected in relation to these unit vectors, why not other unit vectors? Wouldn't we expect that all these things would be connected if you were using different unit vectors? So turns out that the answer is yes. All these things are connected even when you're not looking at standard basis, even when you're looking at other unit vector directions. Any unit vector. All these things relate in morally the same way. Now, what are we going to call that thing? I can't call it a partial derivative. Partial derivatives have already been defined in terms of variables. But all of these properties here, I can give a different name to. And that's what we're going to do. That's what's called a directional derivative. So here's the term directional derivative. Any unit vector at all, and this expression will equal to that expression, which will equal to the slope of the graph, which will equal to the multiplicative factor, all relating to whatever unit vector you're looking at. That's the vector you use as your velocity. That's the vector you dot with the gradient. That's the vector that defines the direction in which you get the slope. That's the vector in which, if you move, then we've got a multiplicative factor. Just like with partial derivatives. So again, not proving these statements, I'm just going to assert that they're true, but I think it's kind of believable because, again, there's nothing special about standard basis vectors other than coordinates, which we're not talking about here. So I hope that's kind of plausible. So again, called a directional derivative, and again, the intuition that you should have is that directional derivatives, that's a rip-off of partial derivatives. Okay. All right. So a couple of pictures here. Slope of the graph, there you go. Slope of the tangent line. Again, with the understanding that you are moving in the direction of whatever vector it is, defining the directional derivative. So as you move in that direction, in other words, if you were to look at a cross-section of the graph, vertical cross-section of the graph in the direction indicated by the given unit vector, then you get a cross-section curve with a tangent line, and that slope is the directional derivative. Is that cool? Let's talk about the multiplicative factor point of view. Again, when we talk about a multiplicative factor, it's what we multiply by input changes to get output changes. Let's see, color choices. I'll use red. Output changes. So multiplicative factor, you multiply by input changes to get output changes. And keep in mind, input changes can either be discrete, finite little distances, right? Or they could be rates of change, either one. Okay. So the directional derivative is that multiplicative factor. It's what you multiply. But if you look over at this algebra over here, what should we call the thing that we multiply by ds to get df? Or the thing we multiply by ds dt to get df dt? In both cases, I think it makes a pretty good sense to call it df ds. Right? You just kind of connect the dots, as it were. It seems like a reasonable thing to call it. So an alternative interpretation of this, saying that directional derivatives are a factor that you multiply by input change to get output change. Another way to say that is directional derivatives are rate of change of the function with respect to distance. So importantly, to be distinguished from rate of change of the function with respect to time. Right? Rate of change of the function with respect to time is a totally different thing. Right? So, for example, let's suppose that I'm walking along a mountain road and F represents altitude, right? And as I move along the road, so other words, as I move in the direction, whatever direction that road happens to be going, I have to go whatever direction the road goes. As I'm moving along the road, there's a couple of things I might be wanting to know. I might be interested in what is the rate of change of altitude with respect to time? How many feet of elevation am I gaining per minute? Right? Am I doing good? Right? I'd like to be able to gain, I don't know, 20 feet a minute? Seems reasonable, right? Am I hitting 20 or am I dragging it at 10 or am I crushing it at 40? This is a relevant number, right? How many feet per minute of elevation? That's derivative with respect to time. And it's something that's relevant to my experience as I hike along this road. Yeah? By comparison, DFDS has got nothing to do with me. That says how much altitude does the road gain per unit distance traveled along the road, and it doesn't matter how fast the person is hiking on it. Right? It's all right. Elevation gain per unit distance. It's just how steep is the road itself. Right. So DFDT is about the traveler, right? And DFDS is independent of the traveler. It's independent of the movement. It's intrinsic to the function itself, and not how you move through it. Does that make sense to everybody? Okay. All right. So again, the interpretation of directional derivative is DFDS. Okay. All right. So let's see an example. I think I have a couple of examples here. Yeah, okay, so starting off with this one, we've got a function here, and I want to know what is the slope of the graph at a certain point in the direction of a certain vector. Okay, and notice the way this is phrased, it's practically straight out of one of the interpretations that we've given for the directional derivative, right? Slope of the graph at a certain point, moving in a certain direction. So right off the bat, slope is directional derivative. One of the other facts on the previous page, directional derivatives are computed by that formula. Right? Just dot product with the gradient. So this is working out pretty fast so far. There's a little tricky bit coming up in just a second, but before we do that, is everybody good so far? Okay. Yeah.
So we take the directional derivative here because it says slope of the graph in that direction, but if it just says slope of the graph,
well, if it said slope of the graph, end of question, then it wouldn't be a very good question because here's a plane. Notice that the slope, if I'm going that way, the slope is pretty steep. It's substantially uphill. But if I'm going that way, it's just not. So it's just it's not a well posed question at that point. Yeah. So yeah, in some sense, the moment that you remove the ambiguity in the question of slope, you're going to have to effectively define then what direction you're talking about. And once you have that direction defined, then it's just a question of finding your unit vector. Yeah. Okay. All right. So here's the little tricky bit. The little tricky bit is, and this is important. Coming back over to here, and let me try to get all this on the page at the same time. Let me clean up the mess. Oh my gosh, there's a lot of stuff here. Oh, I should have gone into the other mode. Anyway, notice in order to interpret the directional derivative as a slope, as a factor, as DFDS. In order to relate it to these equations, the vector's got to be a unit vector. That's an important distinction. Keep in mind, we're generalizing from the idea of a partial derivative, and we made the assertion that partial derivatives talk about standard basis vectors, and standard basis vectors are unit vectors. I can compare other unit vectors to standard basis vectors and say, come on, they're pretty much the same thing. Just different directions, but they're still unit vectors. As soon as I allow non-unit vectors, now I'm talking about different things. And plausibility argument, well, it better be different. Look at this formula. right? If you use a non-unit vector, you're going to, if you have a vector of magnitude 6, then that dot product is going to be 6 times as big as it would have been had you used a unit vector, right? So clearly the magnitude has to matter, and remember that the deal is that to call it a directional derivative, to be able to connect all these properties, v has to be a unit vector. Yeah. Okay, so is that what we have here? Are we ready to go? Are we in business? Do we have a unit vector? No, we don't. Right? We have a non-unit vector. That vector has magnitude 5. So that vector, in order to create a unit vector, I have to divide it by its own magnitude. That unit vector is the one that I can use to define a directional derivative, to compute by dot product with the gradient, all sorts of, the usual stuff that I want to be able to do to relate it back to being a slope. Use that unit vector. Did everybody see what happened? Okay. So you got to be heads up about that. It's real easy to kind of accidentally, by the way this question is phrased is, perhaps not as convenient as the student might prefer, but nevertheless a pretty natural and forgivable phrasing, and very common. Right? People are going to talk this way a lot and say, I'm going in the direct. I just need to define a direction. This vector points the same direction that vector. These point in the same direction, and it's a lot easier to say 3, 4 than it is to say 3, 4 divided by the square root of the blah blah blah. It's just easier. So heads up about that. You do have to be really careful on that point. At this point it's all downhill. We need to compute the gradient, right? So we take that function, we compute various partials, x partial, y partial. We've got to plug in the point in question. 3, 1 is the point where I evaluate. That's the numbers that I plug in for x and for y, and all together then the gradient is 6, 2. Everybody follow that algebra? Took a couple of partials, plugged in some values. And then let's see here. We've already got our unit vector. Right, so you can dot that up at this point. It's just arithmetic, and the slope that we wanted, this dot product, is that value. Okay, so everybody's good. Okay, here's another little quick warning, another little landmine here. You have to be careful with this phrasing in the direction of the vector 3, 4. Let me draw a picture of what this means. And let's see here. I need some space. So let me do this. Okay. In the direction of the vector 3, 4. All right. Well, keep in mind we're starting at the point 3, 1. So we're starting here. That's my A. In the direction of the vector 3, 4. Okay, I got to think about that vector 3, 4. The vector 3, 4 is about like that. Right? The direction that 3, 4 defines, of course, we describe with the unit vector in that direction. We computed all this stuff previously. So this is what we called U. Oh, come on. Okay, does everybody see how I translated this language into that picture? Everybody happy? Here's the mistake a lot of students will make. A lot of students will misunderstand this point, this vector, and it says right here it's a vector, but will misunderstand that as a point, 3, 4. And as a point, 3, 4 is there. Right? So that's, as a point, that's where it is. And then people will kind of sloppily say, well, in the direction of, and it makes it sound like go towards that point. And will then think, oh, I want to go that way, and therefore the unit vector would be like, let's see here, colors again. Unit vector would be this. So that's just not what this says. Right? So heads up on the difference. I mean, it's, again, you can see how someone could accidentally derail just a little bit, again, by interpreting this as a point, not a vector, and then just make a complete misinterpretation. I have the wrong unit vector. Everything's going to crash and burn from there. Does everybody see the risk and the distinction? Everybody's happy? Yeah. Mm-hmm.
But if you did want to solve in the direction of
if the question had said, at the point A in the direction toward the point 3, 4, then this black vector would be the correct unit vector. That's right. Yeah. Yeah. But very importantly, not what this said. Yeah. Yeah. Okay. All right. So anyway, just heads up about that. Be careful. All right. Let's see. One more example. So this was okay, let's see here. Suppose we're interested in this temperature function. And this temperature function, you can see you can plug in different values of x, y, and z. Notice when x, y, and z are all 0, this gives you 85. A warm spot, right? Maybe that's next to the campfire. It's 85. Right? And then as you get further away, as x, y, and z, as this, exponent gets bigger, then this decaying exponential gets smaller, and asymptotically away from the campfire is 60. So a little crisp away from the campfire, nice and toasty at the campfire. Does that make sense to everybody? Okay. All right, so reasonable question one might ask. Suppose I'm sitting here at that point. I guess I'm sitting on an elevated chair. Anyway, where I happen to be, for whatever reason, I'm at that point, and I'm moving in. Oh, got my colors crossed. I'm at this point, and I'm moving with in this direction. And again, direction, right? So we got to think unit vector. I'm going to have to normalize that vector. And I want to know what is dTds? How fast is temperature changing per unit time? And again, this is one of our immediate interpretations of directional derivative. So you want to know rate of change with respect to distance? Boom, directional derivative. And again, as before, directional derivatives computed with that formula, right? Immediately. So again, the colors. The direction is the unit vector in the direction of the given vector. So the given non-unit velocity was this, and you got to normalize it because directional derivatives means unit vectors. And then you're going to have to compute the gradient, right? The gradient. Again, this is just a certain amount of calculus. You're going to have to take various partials of this function, and then plug in the point that you're interested in. That's just partial derivatives, and I'm going to assume y'all are comfortable with partial derivatives at this point. So there's the gradient, and dotting the gradient with the unit vector gives us the directional derivative. Is everybody good? Okay. All right. So I have another heads up warning for you. Gosh, this is uncomfortable. In some contexts, and I want to emphasize, not in Math 219. In Math 219, it's exactly what I've already said, right? But in some other contexts, they don't have this unit vector requirement. And this is a pro-con thing. So going back up to where we were before, here's all the different properties of directional derivative. And I made a big deal about how, well, you have to have, this has got to be a unit vector. Right? So if you take away the unit vector requirement, if you no longer require it to be a unit vector, you do not get slopes. You do not get factors. It's not DFDS anymore. So that's bad news. And so why would anyone want to do this? Why would anyone? I mean, what's the win here? Right? The win is that it still does remain that this expression is equal to this expression. And the reason we would care about such a thing is that this circled in green on the left is a natural thing to want to know. It says, you'll notice, how fast is the function changing? I'm at a certain place and I'm moving with a certain velocity. That's pretty relatable. That's pretty real world. I'm at a place with a velocity. Right? I want to know how fast something's changing. Extremely natural to want to talk about. And it's still computed by this very convenient formula. So this is still a pretty neat thing to want to be able to talk about, even when you don't have a unit vector. Right? So there are those who, 2 seconds. There are those who, in defining the word directional derivative, will define it like this. It's just that expression and no discussion of unit vector and no discussion of slopes and no discussion of DFDS or anything like that. So pros and cons. Again, the pro is this is still a natural thing even if I don't have a unit vector. In fact, sometimes I don't want to know DFDS. Sometimes I want to know DFDT. Right? If I'm tracking my altitude, how many feet per minute am I gaining as I hike? Yeah, I want to know DFDT. I don't care about how steep the road is. I'm caring about my experience along the road. So when you give yourself stronger conditions, you get stronger results, but they only apply more narrowly. It only applies in those special cases where the conditions are satisfied. So do you want to have a strong but narrow theorem, or do you want to have a broad but not so strong theorem? They're just different. Okay, so heads up. Now again, we have to have a uniformity in the course, and so in Math 219, unit vectors required. And I'm making that convention because that's our book's convention. Right? So, unit vectors. But I want y'all to be aware that outside of the course, who knows? It depends on who you're talking to. And by the way, outside of Math 219, I'm one of the other guys. To me, the word directional derivative really, unit vectors, yes, I would like to be able to cite that as well. And to me, I call that a unit directional derivative, which I think makes sense. So why not have two concepts for two separate ideas? But anyway, in Math 219, unit vectors only. Now, you had your hand up first, yeah.
Yeah, so I was going to ask, so if your vector was it has a magnitude of 2, so in your campfire example where you're walking some distance in that direction, if that magnitude was 2, would that just essentially give you the change in temperature for every 2 units of distance?
Yeah, you could think of it that way. You could think of it as it's the rate of change of the temperature if you're walking with speed 2. Right? It would give you DFDT if your speed is 2. You could interpret it also very simply as it would give you 2 times DFDS. Different ways to, sure, absolutely. Yeah, yes.
Why, when we take the unit vector part of it, do the requirements not meet?
Yeah, so you're wondering why these properties no longer hold?
Yeah.
This is what I'm deliberately trying to skirt that. It's a great question. Great question, but I'm gonna dodge it because I don't want to get into the details of the calculations of how these expressions relate to these geometry. We could. It's not hard. It's just time that I don't think is well invested. Being a unit vector is required there. Now, a short answer is if you didn't have to be a unit vector, where you could put a vector of whatever magnitude, well then you could get whatever value. You just make this vector longer or shorter, you keep getting different values. And all those different values can't all equal to the slope. Right? So in some sense we know there's really only one magnitude that could work. And I'm just going to, the way I want to approach things here is, would you believe me, by analogy with partial derivatives, that it ought to be magnitude 1? I think that's a reasonable. Is that satisfying? Okay. Yeah. All right. Okay. So yeah, heads up. All right. Yeah. So let's talk about how to maximize directional derivative. Turns out that there's a really interesting answer to this question. Arguably, the answer is more interesting than the question, which happens sometimes. So anyway, here's the question. Suppose we have a multivariable function. So multivariable in the sense that the domain has multiple variables, right? So yeah, multivariable function, and we're looking at some point A. Here's the thing. If you're sitting at that point A, there's a bunch of different directions that you can move. And again, I'm going to use unit vectors to represent directions. And these are just some of them. Of course, there's an entire circle of different directions, in fact, that you could move. Of all of those directions, again, starting at the point A, of all of these different directions, which one is going to make the directional derivative? Let's see here. Colors. I'll use yellow. Which one is going to make the directional derivative, namely how fast the function's changing? Which one's going to make that as big as possible? So, why would we want to know such a thing? Here's a easy for example. Maybe F represents temperature, and I'm here, and I'm cold. Well, which way do I walk to warm up as fast as possible? I don't want to walk away from the heat. I want to walk directly toward the... Which way do I walk so that my temperature increases as fast as possible? Right? Reasonable question. And you can think of any number of different sort of physical motivations or applied motivations for why you'd want to do such a thing. All right. Does everybody understand the question? Okay. Now, before I get to the answer, I want to interpret the question a little bit. Directional derivative. Keep in mind, one of our interpretations of directional derivative is how fast is the function changing per unit distance? Okay, well, if you want to maximize how fast the function is changing, you want to maximize, and by the way, there's always going to be a direction in which it's increasing, not decreasing. So if you want to maximize the amount that the function is increasing, pretty reasonable to think that this vector that we're looking for here, whatever vector that's going to end up being, that vector is the direction of fastest increase. It's the direction in which the function's increasing the fastest. Okay? Increasing the fastest. Is that cool? Yeah. Okay. So that's one way to interpret it. Now, here's another way to interpret it, and this one I'll remind you is narrow. Directional derivative is the slope of the graph. And that's true, and that's fine, and you could see that if you interpret the directional derivative as the slope, you want to maximize the slope, you want to maximize, as you're moving through the domain, I want to find which way do I go that makes, as I go follow the graph, that I want to go up as steep as possible. So steepest ascent, you might call it. Different way of looking at it. But I claim this is a narrow point of view. And so, for my own personal preferences, I tend to not like this phrasing as much because this phrase only makes sense if you're looking at a graph. Right? Keep in mind, directional derivatives are not just the slope of whatever geometric object you might happen to be looking at. Directional derivatives are slopes of graphs, specifically and exclusively. Right? So this interpretation, this language, I'll say it this way, this language assumes an interpretation that you might not be taking. You might literally be walking around in the woods cold trying to get warm as fast as possible. There's no graph. It could be entirely flat ground, right? Entirely perfectly flat. What do you mean steepest descent? Doesn't really fit the context, right? What I like about this other one is it always makes sense. You can just interpret it accordingly. Direction of fastest increase. Well, if you're trying to make temperature increase as fast as possible, well, there you go. Cool, no problem. And, on the other hand, if you were looking at altitude, yeah, we're trying to make altitude increase as fast as possible. That means exactly the same thing as steepest descent. So this is really the more general interpretation, I'd say. But sadly, unfortunately, this is the more common term. Steepest descent is the more common term. So, oh gosh, what did I just do there? Okay. This is the one that you're going to hear more often. Steepest descent. Okay. So how do we find it? And well, here is our formula for the thing we're trying to maximize, directional derivative. It's a dot product. Here's how you compute a dot product. This is the thing we're trying to maximize. Notice we've got a gradient vector here. The gradient vector. What happens to the gradient vector as I entertain different possible directions I might move? What happens as I'm at this point and I look that way, but then I look this way, then I look that way. I'm considering all these different. I haven't moved yet. I'm just thinking about moving in all these different directions. What happens to the gradient vector? Nothing. The gradient vector only depends on where you are. Right? It's evaluated at the point. It is independent of what you're thinking about. Right? So the magnitude of the gradient doesn't change at all. It's a constant. It's just a constant. Of course, the magnitude of the unit vectors are 1. So that factor goes away. And so if you think about it, then really, if you're trying to make this as big as possible, really you're trying to make that as big as possible. Another way to say that is you're trying to make cosine theta as big as possible. So the question boils down to, how do you maximize cosine? And well, that's easy. Cosine is maximized when theta is 0. And specifically then that means that the angle between the gradient and the direction of fastest increase, that angle should be 0, which means my picture is bad, right? Because I had to draw it not being 0 so I could draw that there is an angle, right? But if the answer is that theta is equal to 0, then what I really need is I need for my vector, my direction of fastest increase, is the direction that the gradient vector points. Is that cool? Everybody's happy? Okay. All right. Cool. So that's how you maximize a directional derivative. Just go in whatever direction the gradient says. The gradient is the answer in some sense. Natural next question. Okay, so I'm supposed to go in that direction. How much is the function going to be increasing? How quickly am I going to be getting warmer? How fast will I be gaining altitude if I go in that direction? Whatever your context is. So easy calculation again. Directional derivatives are computed by dot product with the gradient. We've already agreed that our optimal direction is the direction of the gradient, aka it's the gradient divided by the magnitude. Then we find that we've got gradient dot gradient, and that's magnitude squared. So I have magnitude squared divided by magnitude, and that gives me that the directional derivative I'm interested in is the magnitude of the gradient. Everybody good? Oh, yes.
So cosine of theta could also be maximized at like pi?
Well, it's minimized at pi. Yeah, then you get -1. And that if you wanted to find the direction of fastest decrease, then yeah, that's what you get, pi at that point. Which, if you think about it, if it's increasing as fast as possible that way, stands to reason it's decreasing as fast as possible. Yeah, totally. Yeah. All right. Yes.
So decreasing would just be like negative magnitude of gradient amount.
Yep. That's right. Exactly. Oh. Right. Okay. Yeah. So, I like to rephrase the above, and I already said that it's kind of, the answers are kind of more interesting than the questions. But I'm going to say it differently here as this gives us a geometric characterization of the gradient. And we started off talking about directional derivatives, but in fact, what we've really learned here is really valuable information about the gradient vector. The gradient vector was the answer to both of the previous questions. The answers were whatever direction the gradient points and whatever the magnitude of the gradient is. Those were the answers to the questions on the previous page. So, like I said, I call this a geometric characterization of the gradient. It's the unique vector that points in the direction of fastest increase and whose magnitude is the, again, what you might call the slope or the maximum directional derivative in that direction. So, what's really interesting about this is if you look back at how we defined the gradient, and this happens sometimes. It's kind of cool when this kind of thing happens. We defined the gradient as kind of just an algebraic thing, right? It was we were looking at linear approximations, and we had too many terms, and it was getting kind of bulky, and so we said, notice this looks just like a dot product, and so I just made up this thing called the gradient vector for notational convenience as the vector of partial derivatives. It was purely for notational convenience. And what we see now is that it's geometrically natural, right? Its direction and its magnitude, both of its geometric traits, are answers to important questions. And I think that's pretty neato. Unexpected geometry. How about that? Okay, so here's an example. So suppose that you're looking at a hill. So there's your hill. It's in the shape of the graph of a function. So that means z equals f. Height is a function of maybe longitude and latitude, but let's just say x and y. I'm sitting at a certain point. I'm here on the hill. That's me. And now where is that point? Well, it's a point on the graph, but that point corresponds, of course, to certain values of x and y. And so I'm going to say it's the point above 1, 3. And let me just point out, that's how people talk, right? That's obvious. If I say I'm at 1, 3, I don't mean that I'm buried 20 feet underground under the hill, right? If I say I'm at certain longitude and latitude, it's understood that I'm on the ground, whatever the altitude is at that longitude and latitude, right? So the altitude of Duke campus is somewhere in the range of about 300 feet, I think. So if I were to tell someone, I'm on Duke campus, longitude this, latitude that, they know I'm on ground altitude. All right, so be aware, and I'm kind of getting ahead of the game a little bit here, but be aware that very often we'll conflate the point on the graph with the point in the domain that corresponds to that point on the graph. Because very often this is what's actually happening, but very often this is the one that's easier to talk about. Because that's the inputs to the actual function. So 1 and 3 is what actually goes into the function there. Does that make sense to everybody? I hope it's okay. Yeah. All right, so, which way is uphill? Reasonable question. Given where I am, which direction do I hike to get to the top the fastest? If you're into that sort of thing. So, which direction you go? Gradient. Always in the direction of the gradient. Right? And so, plug in, take the appropriate partials, x partial and y partial, plug in your point, 1, 3, and there's the direction that the function increases the fastest. There is the direction of steepest descent. And you'll notice it is kind of like that. It's kind of, and you can see from this way I've got this drawing here anyway, that is pointing into the hill. So again, it's pointing in the domain, right? If you were at this point, you wouldn't literally go horizontally. You wouldn't start digging, obviously, right? They're just saying move on the hill in such a way that your corresponding point in the domain is going that way. Okay. All right. Everybody happy with this? Okay. All right, let's see here. So level sets. Yeah, we'll see how far we get here. Yeah. Sometimes we're not looking at graphs. Sometimes we're looking at level sets. So, is there a reasonable interpretation of the gradient? We've got a fantastic interpretation of the gradient in the context of graphs, right? So, if you're looking at a level set, though, then is there any relevant geometry? What's a relationship? Is there any relationship between gradients and level sets? It turns out there's a fantastic one. So, here's a multivariable function. We are drawing here a picture of the domain. Right? R3 is the domain, at least as I have it in this picture. So this is a function from R3 to R1. This is not a graph. Right? And so in particular, we are looking at a level set here. We're looking at where f is equal to some fixed constant value. Okay. So there's our picture. And we're sitting at a point that's on that level set. Okay, so here's the innocent observation I'm going to make. If I were to move along the level set, now I'm trying to draw that to be entirely on this level set, f equals c. I'm going to make the innocent observation that as I move along the level set, f remains constant. Because I'm on f equal. That's the whole point of this set. This is the set where f is always that same constant. That means that as I move along this blue curve, in other words, from this orange point as I move with that velocity, that tangent vector velocity, my directional derivative should be 0. Because I'm moving with a velocity, yeah, sure, but that's the velocity that keeps me on this curve that is entirely on the level set where the function's not changing. Right? So that directional derivative should be 0. And by the way, ditto all of the other tangent vectors. Any tangent vector, directional derivative should be 0. But the thing is, directional derivatives are computed with dot products with the gradient. That means that the dot products with the gradient are all 0 when I'm looking at tangent vectors. And that means that, let's see here. Here we go. That means that the gradient vector has to be perpendicular to all of those tangent vectors. And there's a really nice way to represent that. Again, if you have all these are tangent vectors. Let me zoom back in. All these are tangent vectors. What vector could it be that's perpendicular to all the tangent vectors? Well, the gradient vector, perpendicular to all those tangent vectors, must then be perpendicular to the surface itself. And this is the neat interpretation. Gradients are always orthogonal to level sets. So they point uphill on graphs. They are orthogonal to level sets. Everybody good? Makes sense? Yes.
S isn't supposed to have any curvature, right?
I'm sorry, one more time.
The surface S isn't supposed to have any curvature.
Oh, yeah, no, the surface definitely has curve. Yeah, the surface might be all kinds of curved. So what we're talking about, when we say that a vector is perpendicular to a surface, what we really mean is that the vector is perpendicular to the tangent plane of the surface, which I appeal to your geometric intuition, means it's perpendicular to all the tangent vectors. Does that make sense?
Yeah.
Yeah, okay, yeah. Cool. Okay, and I think we're out of time, so this is a good place to draw the line. We will pick up here on... Oh, no, we won't. Monday's the exam. Don't forget. Good luck to everybody studying for the exam. The usual... We'll meet right here at the usual time, right? Everything just right here in class. And, good luck to everybody. See you later.